Hello, everyone. Today we're going to talk about part 3 of forces here at Xhyn Physics. Well, forces part 3. So if we have an Atwood machine, which is an ideal case, and what exactly is an ideal case? It's a case that is not realistic at all, but that can be useful to explain theories and concepts in physics, right? We physicists, we create situations that are much easier to deal with than in real life in order for us to have some understanding in the chaotic motion particles in matter in the universe, right? The universe is much more complicated than the ideal case. So the Atwood machine, we're ignoring the moment of inertia of the pulley, we're ignoring the mass of the string, we're ignoring friction. So if we ignore all that and we run the simulation, we get the Atwood machine. The tension of the string of the Atwood machine is the following. Assuming M1 is heavier than M2, um, since M1 is the heavier box, um, we can find the tension on M1. Remember that in the forces part 2 video, I explained how to get the net force and acceleration on that one machine. And that you can find on forces part 2. So if we were looking for tension of the string basing off M1, the heavier mass, we're going to get that because M1 is the heavier mass, its acceleration will be negative, and its acceleration is equal to the tension up minus the weights down, and then you get a net force of negative ma. You can find the tension by bringing the mg to the left, so tension then becomes m1g minus m1a, which simplifies to m1 times g minus a. Since m2 is the lower mass, its net force is equal to m2a. This time, positive acceleration because since m2 is the lighter mass, m2 will be going up, and the pulley will be rotating counterclockwise in this case. We can find the tension likewise as m2g plus m2a, and then you get that the tension basing off m2 will be m2 times g plus a. Now, believe it or not, the math is perfect in this case, and you should get the same tension on both ways. Isn't that amazing? Here we have Jürgen Zervina contemplating these beauties in mathematics. In the video forces, part 1, I believe, and also in part 2, we talk about forces, we talk about direction of forces. But in physics, the direction of the net force is always from the positive x-axis. So if you have this first example, where you have an angle theta from the positive x-axis, the direction would just be theta. In the other example, where the arrow is pointing somewhat to the left and up, you're going to have to do 180 minus the angle theta to get the direction from the positive x-axis. And then if the net force vector is down and to the left, then you're going to have to do 180 plus the theta to get the direction from the positive x-axis. Then if the direction is down and to the right, you can do 30, 60 degrees, how many degrees in a circle, minus theta, or negative theta, because it's convenient to do this way. Inclined planes with box at rest. So if we have a box on a surface, flat surface, we get the normal force and the weights and the friction the way we found in the early videos. But then when the box is placed on an incline, things are slightly different. Let's suppose that the box is at rest. If the box is at rest, it means friction is up the incline. The weight of the box is just mg. The normal force is mg cosine theta. Why is that? Because the weight is the hypotenuse of that triangle inside the incline. And that angle is equal to the angle of the incline. So that being said, because the box is not accelerating perpendicular to the inclined plane, it means that mg cosine theta in a downward direction will equal the normal force. Now we also know that the force down incline is mg sine theta. So that's the component of the weight down the plane. And friction, it will be equal mg sine theta when the box is at rest because the force down incline cancels out with the force up the incline, which is friction. Critical angle. The critical angle is the angle at which the box on the inclined plane begins to slide. So you agree with me that if the box is at rest on the inclined plane, there will be a point, there will be an angle on the incline where the box will begin to move. And any angle of the incline greater than critical, the box will move. And any angle of the incline less than critical, the box will remain at rest. This angle can be found with the following. We know mg sine theta is equal to friction. Mg sine of theta equals to coefficient times normal force. Mg sine theta is equal to normal force, which is mg cosine theta with the mu in front. Mu is the coefficient of friction, which is a coefficient of the ratio of friction over normal force. And coefficient of friction depends on which two surfaces are rubbing against each other. In this case, the box and the surface of the inclined plane. So sine of theta equals mu cosine theta. Sine of theta over cosine theta, and you get mu. Tangent of theta, we get mu because sine over cosine is tangent, and inverse tangent of mu equals theta. So that, if you know what the coefficient of friction is, you can find the critical angle, and believe it or not, it does not depend on the mass of the object. So you can put a really heavy object over the incline, or a really light object over the incline, and the inverse tangent of coefficient of friction will still equal the critical angle. If the box is moving up incline, friction is down incline. If the box is moving down incline, friction is up incline. So if the box is moving down incline, friction is up because friction is always points in the opposite direction as the force down as the direction where the box is moving. If the box is moving up incline, friction is down incline. The net force and acceleration of the box moving over incline is the following. So in a general equation, in the general situation where the box is moving, force down incline minus friction will get you net force. And of course, you can do net force, which is force down incline is mg sine theta minus mu mg cosine theta. And the net force over the mass of the box will give you acceleration just like we talked about it earlier. So this then concludes our forces part 3, and there's going to be forces part 4. Thanks for watching.